Okay, so this now is 2012, yes, 2012, question 2. So part A was the rain falling and it was hitting a windscreen of a car. And we had to find the angle with which it appeared to strike the windscreen. So I was told that the rain was falling at an angle of 20 degrees to the vertical. So if I said this is my vertical line, that black dotted line is the rain. So this angle in there is 20 degrees. And if I break that black dotted line up into its two components, this is and it's falling at a speed of 25. This is the opposite to the angle. So this will be 25 sine 20, and of course this one will be 25 cos 20 because that's the j component. So that will give me the velocity of the rain. So my velocity of the rain is equal to, and it's positive in that direction, so 25 sine 20 on the I minus 25 cos 20 on the j. The car is travelling along at 20 in a westerly direction, so the velocity of the car is minus 20I plus 0j. Okay, so it says find the angle at which the rain appears to strike the car. So the velocity of the rain relative to the car, I'm going to have to do a VRC. And if you work that out, you get 28.55 in the I direction minus 23.49 in the j direction. So that's your VRC. Now then, if you look at that angle there, well, let's finish it off and get the speed and the VRC modulus and the direction. So we'll do all that. So the direction, remember, will be arctan of 23.49 divided by 28.55, and we end up with 39.45 degrees. So this direction here, the direction of the rain relative to the car, is 39.45 degrees. Okay, so let's just have a look. Now I'm nearly there, and I'm nearly there. It says find the angle at which the rain appears to strike the windscreen. So if the rain is coming down like this, okay, that's how it appears. This is the angle with we'll say the VRC. This is the angle that the rain appears to make with the car, but the windscreen is at a different angle to that again. So I'm just going to redraw this. So this, my x and y axis, will say my ij axis. Here's this rain now striking down here, and it's hitting at an angle of 39.45 degrees. I'm going to call that alpha. So this is alpha. Now then, here's the windscreen of the car. So the windscreen of the car is that kind of direction here. So that would be your black car. That's the windscreen. It tells me that the windscreen of the car makes an angle of 32 degrees with the vertical. So I'm told that in the question. So this is 32. So if I want to find the angle with which the rain appears to strike the windscreen, this is the angle that I want. This one here. I'm going to call that one theta. So if I'm going to find theta, I'm going to need this angle here. I'll call this beta. So theta is equal to beta plus 32. Right, so tracking back, I know that, I know what alpha is. I know this is 39.45, which means this, of course, is 90 degrees, the two black lines. So I'm going to be able to get this one here. I'll be able to get angle dot. So I'll take 32 from 90 to get dot. And then I'll be able to find beta, because that angle there will be 180 degrees. Okay, so it's a bit long-winded, but you'll get there eventually. So what's angle dot? Angle dot will be 32 minus 90, which gives me 58. So this angle here is 58. This entire angle then here, of course, will be 180 degrees. So alpha, which is 39.45 plus 58 plus 32, that gives me 129.45. And if I take that from 180, I'll end up with 50.3 50.55. So beta is 50.55, which means then that theta is going to be 82.55. So it was just a bit kind of complicated at the end. That windscreen was a bit silly at the end. But anyway, don't worry too much about that. The other bit was the more important bit. Now, part B, however, caused problems with the diagram. So that's what I want to do now. So what we have is at noon, a ship A is 50 kilometres north of B. So I'll put B, A. Ship A is travelling southwest, B is travelling due west. You've got to find the magnitude and direction of the velocity of B relative to A. Okay, so you find VBA. And what was it now? VBA was 7I plus 24J. So you found that, okay. And then, of course, you got the magnitude of it and the direction. So your magnitude was 25. And the direction, of course, was arctan 24 divided by 7, which gives you 73.74 degrees. So 73.74 degrees to the y-axis. Okay, so we'll put this VBA into the diagram. In it goes. I'm going to put it in this blue line here. There it is. So this is my VBA, okay. It's making an angle, of course, of 73.74 with, I'll put it over here out the way for a moment, I'll call that alpha. Now, at what time, it says they can exchange signals, these two, for when they're 20 kilometres apart. So, at the beginning, they're 50 kilometres apart, so this black line here is 50 kilometres. Now I'm going to drop a perpendicular from A down onto that blue line, and that red line there would be my closest distance. Okay. I can find closest distance then because I have this angle obviously here, alpha. I'll be able to get in here. I'll call that one maybe theta. So, and I'll know then that the sine of theta is d over 50. So d is equal to 50 sine theta. And when you do that, at 50 sine of theta, which of course I'd have to have taken alpha from 90, I end up with a d of 14. Okay, so d works out at 14. I'm going to put that in here. Okay, so I get my closest distance. They can exchange signals when they are 20 kilometres apart. So what I'm going to do is draw a circle from A, 20 kilometres radius, cutting that blue line. Like so. And then, if I drop a line from here to here, and from there to there, where it cuts the blue line, this is when they can exchange signals along that blue part there. So I'll call that distance here maybe x and that x. And we would know how to find x. So the question says, how long can they, I'm going to do part 3 of the question first. How long can they continue to exchange signals? Okay, so they start exchanging signals here as far as there. So they can exchange signals for, we'll say time is equal to distance over speed. And of course it would be relative distance over relative speed. So that's going to be 2x over, and I know what the relative speed is, I'm after finding that 25. So your first job is to get x. In order to get x, remember your red lines are 20. So you'll use Pythagoras to get you x. And when you do that, you get, what do you get? You get 1.284, I think, is it? So 20 squared minus 14 squared, and then get the square root of that, and that gives you 14.28. Okay, so that x is 14.28. We've two of them. and we're going to divide it by 25, which gives us 1.14. 1.14 hours. Now, 0.14 hours is no 8.4 minutes, we'll say. So 1 hour, 8, is it exactly, I think it's a little bit more than that actually. So the 2x, let me just go back over this figure again. 20 squared minus 14 squared, and get the square root of the answer. 20 squared minus, 20 squared minus 14 squared gives me 204. And if I square root that answer, I get 14.2828. Now, if I double that to get 2x, is 28.56. So 2x is 28.56 over 25, which gives me 1.1426. Right, I'll just 1.1426, be a little bit more accurate. Okay, now that's 1 hour, 0.1426. If I multiply that by 60, that gives me 1 hour, 8.56 minutes. Okay, so they can exchange signals for 1 hour. We'll say 1 hour 9 minutes is what the answer was accepted as. So this is how long they can exchange signals for. Now the first bit actually of the question caused a few more problems. At what time can they begin to exchange signals? Okay, so this position here is when it all begins. So from here to there, they cannot exchange signals. But once they get within this triangle here, then they are exchanging. So if I could figure out here what that distance is, then I could work out the time to get from there to there, because of course I'd use relative distance over relative speed. So my job first of all is to find out what is that little distance there, that bit there. Looking at this triangle, I know that that black line's 50. I know that this is 14. So I could find that total distance from there to there. So I have that this, I'm just going to redraw this, 14, and that's a black line here of 50. Okay, so I have 50, 14, and then I have that part on the blue line is from the origin, we'll say, as far as there. And if I call that little bit there, maybe if I call it y, then from there to there is x plus y. So that bit here is x plus y, where y is this little starter bit there at the beginning. And if you do that, what do you get for x plus y? You get 50 squared minus 14 squared, and get the square root of your answer, and you end up with 48. So x plus y is equal to 48 by Pythagoras. Now we already know here what this distance is. X's distance is 14.56, or sorry, 28.56 divided by 2 is 14.28. So x is 14.28, y is 48, or x plus y is 48, which means that y is 33.72. So this little distance along that blue line is 33.72. So how long does it take to travel that distance before they can start communicating? So the time is going to be relative distance, which is the 33.72, divided by the relative speed, of course, which is 25. So if I divide that by 25, I end up with a time of 1.3488 hours. And of course, if I turn that into minutes, what's that? 0.3488 multiplied by 60. That'll give me 20. So the time is going to be 1 hour, 20.9 minutes. So I'll say 1 hour, 21 minutes is how long it takes to get from there to there. Now, on the clock, at what time then do they start communicating? Well, if it all started at 12 noon, 1 hour 21 minutes later means that on the clock, the time is 13:21. So they start communicating at 13:21. That continues for 1 hour 9 minutes, and then they're out of range again.